Hello friends, welcome to True Academy. In the last lecture, we have discussed up to question number 5. So we will discuss question number 6 onwards in this particular lecture. So basically, we are discussing the problems on the tangential and normal velocities and acceleration. So let's start our discussion. So what is given in the question is that a point moves along an arc of a cycloid, okay, in such a manner that the tangent at it rotates with a constant angular velocity. So the angular velocity is equal to constant. Okay, so angular velocity we can write as omega is equal to d psi upon dt. Psi is the angle of rotation is given as constant. So let us consider this as lambda. Okay, sorry, let us consider this as c. Let us take the constant as value c. So this is equation 1. Also, it is given that um, the point moves along the arc of a cycloid. Okay, so the intrinsic equation of cycloid is S is equal to 4a sine psi. Okay, let us take this as equation 2. Moves with a constant angular velocity so that the acceleration of moving point. So we have acceleration is given as d2s upon dt square the whole square plus v square upon rho whole square under root. What we have studied in the last lecture is that acceleration is given as tangential acceleration square plus normal acceleration whole square under root. So we have at is equal to d2s upon dt square and an is equal to v square upon rho. This is the normal acceleration and this is tangential acceleration. So here we are having s is equal to 4a sin psi. So we have ds upon dt is equal to 4a into differentiation of ds upon dt we can write as is equal to ds upon d psi into d psi upon dt. And d psi upon dt we are having as c. So this is equal to ds upon d psi is 4a cos psi into ds upon d psi upon dt is c. So this is 4ac cos psi. 4ac cos psi. This is ds upon dt. Let us differentiate once more. The d2s upon dt square is equal to minus 4ac into cos c ka minus sin psi. So this is sin psi into d psi upon dt. D psi upon dt is c. This we can write as c. This is equal to minus 4ac square sin psi. So this we are having, and let us write down here. So we have d2s upon dt square is equal to minus 4ac square sin psi. Now let us find v square upon s. So we have this as ds upon dt is v. So we have v square upon rho is equal to, and rho we are having, rho is equal to ds upon d psi. So we have s is equal to 4a sin psi. So ds upon d psi is 4a cos psi. So we have v square upon rho is equal to v we are having as this. This is 4ac cos psi whole square. Upon rho की वैल्यू क्या है ये 4a cos psi. So this we are having as 4a c square cos of psi. This is equal to v square upon rho and d2s upon dt square is equal to this one. So let us put this value in this Excel. Acceleration is equal to d2s upon dt square is this one. So minus 4ac square sin psi whole square plus v square upon rho का whole square. So 4ac square cos psi whole square under root. Okay, so this we are having as 4ac square whole square into sin square psi plus cos square under root. And sin square psi plus cos square psi is 1. So this is equal to 4ac square. Acceleration. So that the acceleration of moving point is constant in this is constant. Okay, so the acceleration of the moving point is constant in magnitude. Okay, so let us discuss question number 7. So what is given in the question? Rate of change of direction of velocity. Okay, so let us consider a curve like this. Let us consider a curve like this. Let us consider a point P. So let us draw a tangent at this point P. Okay, so the direction of tangential velocity is v in this direction, and let this tangent makes an angle of psi with the horizontal. Okay, so this is horizontal. So we have rate of change of direction of velocity of the particle. So rate of change of direction. The rate of change of direction of velocity. Direction of velocity is equal to d psi upon dt equal to constant. So this is similar to the previous question. Okay. Prove that acceleration is constant in magnitude. This is similar to the previous question. Because in last lecture also the d psi upon dt is constant. So what we have to find? So since it is a cycloid, so the intrinsic equation of the cycloid is s is equal to 4a sin psi. So we have to find d2s upon dt square and v square upon rho. Then acceleration is equal to d2s upon dt square ka whole square plus v square upon rho ka whole square ka under rho. On simplifying this, we will get 4ac square. This is equal to constant. So what hence the acceleration is constant in magnitude. Constant in magnitude. This is similar to previous question. Okay, so let us discuss question number 8. How we can solve this? A point moves in a plane curve so that tangential acceleration is constant. So we have the tangential acceleration as dv upon dt is equal to constant, and the magnitude of tangential velocity. The tangential velocity upon magnitude of tangential velocity and normal accelerations are in a constant ratio. Okay, so let us find the ratio. The tangential velocity upon normal acceleration are in constant ratio. So let us consider this constant as mu. So we have the tangential velocity as v and normal acceleration v square upon rho is equal to mu. So we have rho upon v is equal to mu. So rho we can write as ds upon d psi upon dt. Sorry, ds upon dt. ds upon dt equal to mu. So now we are having is that dt upon d psi is equal to mu. So we have d psi upon dt as 1 upon mu. Okay. And from here we have rho is equal to mu into v. Okay. So and we are having d psi upon dt as uh, 1 upon mu. So now we can simplify this as dv upon dt is constant. So let us take this as lambda. So we have dv upon d psi into d psi upon dt is equal to 1 upon mu, sorry, lambda. This is equal to lambda from equation 1. Let us take this as equation 1 using equation 1. And this is equation 2. And let us put this value here. Dv upon d psi into d psi upon dt is 1 upon mu equal to lambda. So we have dv upon d psi is equal to lambda into mu. Okay. So we have dv is equal to lambda mu into d psi. Let us integrate this. So we have v is equal to lambda mu into psi plus k. Okay. So let us put this value in the rho is equal to mu v. Let us put this. We have rho is equal to mu into v. So rho is equal to mu into lambda mu psi plus k. So we can write rho as ds upon d psi is equal to lambda mu square psi plus k into mu. So we have ds is equal to lambda mu square psi d psi plus k into mu d psi. This we can integrate as s is equal to lambda mu square into psi square upon 2 plus k mu into psi plus c. So this we can write as uh, s is equal to lambda mu square upon 2 psi square plus k mu into psi plus c. So this is equal to a psi square plus b psi plus c. This is the intrinsic equation of curve. Okay, where a is equal to lambda mu square upon 2, b is equal to k mu, and c is equal to t. Okay, so this is the S is equal to a psi square plus b psi plus c is the intrinsic equation of the curve. Okay. So let us discuss question number 9. How we can discuss this? The particle moves in a plane in such a manner that its tangential and normal accelerations are always equal, and its velocity varies as with. Now the tangential manner such that tangential acceleration is equal to normal acceleration. Normal acceleration. Okay, are always equal. So we have dv upon dt is equal to v square upon rho. So this we can write as dv upon ds into ds upon dt equal to v square upon rho. This we can write ds upon dt we can write as v. So v into dv upon ds is equal to v square upon rho. This we can cancel. So dv upon ds is equal to 1 upon rho is ds upon d psi. This is equal to d psi upon ds. This gets cancelled. And this is v now. V is also there now, v. So we have dv upon v is equal to d psi. Let us integrate this. So we have log of v is equal to psi plus a. So we have v is equal to e to the power psi to e to the power a. A dash, let us take this as a dash. So v is equal to a e to the power psi. Okay. And its velocity varies as the exponential tan inverse s upon c. So we have velocity is proportional to the e to the power tan inverse s upon c. This we can write v is equal to k e to the power tan inverse s upon c. So let us put v is equal to a e to the power psi. So a e to the power psi is equal to k e to the power tan inverse s upon c. So let at s is equal to 0, psi is equal to 0. So let us put this to a into e to the power 0 is equal to k e to the power tan inverse of 0. So from here we are having a is equal to k. Okay, so let us put a is equal to k. This means this gets cancelled. So we have this equations become, let us put a is equal to k. So at the place of k we are having a. So this gets cancelled. So from here we have e to the power psi is equal to e to the power tan inverse s upon c. So we have psi is equal to tan inverse s upon c. So from here we have s upon c is equal to tan of psi. S is equal to c tan psi. Okay, so this is the path. This is the path of particle, which is equation of common catenary. Common catenary. Okay, so this S is equal to C tan psi is equation of common catenary. Common catenary. Okay, let us discuss question number 10. How we can solve this? So we have point moves in a plane curve, so that is tangential and normal accelerations are equal and the angular velocity of the tangent is constant. So how we can solve this? So we have the tangential and tangential acceleration is equal to normal acceleration. Normal acceleration. So we have dv upon dt is equal to v square upon rho. V square upon rho. So we have v dv upon ds. This we can write like this. Is equal to v square upon rho. So v gets cancelled. So we have dv upon v is equal to ds upon rho. So we have dv upon v is equal to ds upon d psi. This is equal to d psi. So we have log of v is equal to psi plus a dash. So we have v is equal to e to the power of psi into e to the power of a dash. So this is equal to v is equal to a e to the power psi. Okay, and the angular velocity of the tangent is constant. So this has, we are having angular velocity of the tangent. So let us take the curve like this, P. So we have draw a tangent at point P, and this tangent makes an angle of psi. So we have the angular velocity is equal to d psi upon dt. Okay, this is the angular velocity is constant. D psi upon dt is constant. So we have v is equal to So let us write this like this. So we have v, we can write as ds upon dt. The ds upon dt is equal to a e to the power psi. So we can write this as ds upon d psi into d psi, d psi upon dt, a e to the power psi. So d psi upon dt is constant. So let us take this as c is equal to c. So this we can put as c. D psi upon dt is c. So we can write this as ds is equal to a upon c into e to the power psi d psi. Integrate. So we have s is equal to a upon c into e to the power psi plus b. Okay. So we have the equation as s is equal to we have the equation as s is equal to a upon c e to the power psi plus b is the curve on which particle is moving. Okay, so let us discuss question number 11. What is given in the question is that a particle describes a circle of a radius r with a uniform speed. Okay, this is a circle of radius r and it is describing this with a uniform speed and we have v is equal to constant. Okay, so we have v is equal to constant. So we have dv upon dt is equal to tangential acceleration is equal to 0. This means d2s upon dt square is equal to 0. So we have the acceleration as d2s upon dt square का whole square plus v square upon rho का whole square का under root. So this is 0 d2s upon dt square. So this gets vanished. So we have v square upon rho. And for this circle, we have rho is equal to r. Rho will be radius. So we have v square upon r. So the acceleration at any point, any point, um, any point of the path is v square upon rho. Since the acceleration is v square upon r, so it will be directed towards the center. At any point, the acceleration is directed towards the center. Okay, so let us take any point on this circle. So the acceleration will be directed towards the center and it will be equal to v square upon r. Okay, and it is directed towards center of the. Okay. So now because the tangential acceleration is 0 because v is equal to constant, this means dv upon dt is equal to 0 because v is constant and v we can write as ds upon dt. So we have d upon dt of ds upon dt is equal to 0. So we have d2s upon dt square equal to 0. This means tangential acceleration is 0. The tangential acceleration is 0. We are left with normal acceleration. Okay. So let us discuss question number 12. How we can solve this? A particle is describing a plane curve if the tangential and normal accelerations are each constant. So we have the tangential acceleration as dv upon dt is equal to constant. Let us take this as lambda. This means v is equal to lambda t plus c1 on integration. So let us take this as equation 1. And we have normal acceleration is also constant. V square upon rho is constant. Let us take this as mu. So we can write this as v into v upon rho is equal to mu. So v into ds upon dt upon ds upon d psi is equal to mu. So we have v into d psi upon dt is equal to mu. So d psi upon dt is equal to mu upon v is equal to mu upon v we are having as lambda t plus c1. Lambda t plus c1. So this we can further integrate as d psi is equal to mu into dt upon lambda t plus c1. This we can integrate as psi is equal to mu upon lambda log of lambda t plus c1 plus c2. Okay. So what we are having is, let us find the constant of integration c2. How we can find this? So let at t is equal to 0 we have psi is equal to 0. Let us put this 0 is equal to mu upon lambda into log um, lambda t, sorry, lambda t is 0, so lambda into 0 plus c1 plus c2. So we have c2 is equal to minus mu upon lambda log c1. Okay, so this is the value of c2. Let us place it here. So we have psi is equal to mu upon lambda log of lambda t plus c1 minus mu upon lambda log c1. So psi is equal to mu upon lambda log of lambda upon c1 into t plus 1. So we are having as psi is equal to mu upon lambda log of 1 plus lambda upon c1 into t. So this we can write as psi is equal to a log of 1 plus bt, where a is equal to mu upon lambda and b is equal to lambda upon c1. So this is the equation. क्या दिया क्वेश्चन में? If the tangential and normal accelerations are each constant throughout the motion, prove that angle psi through which the direction of motion turns. So the angle psi is given as, we can write it here as the angle psi through which the direction of motion turns in time t is given by psi is equal to a log 1 plus bt. Okay, this is the value of psi. Okay, so we have discussed up to question number 12. Okay, so we will start next topic in the next particular lecture. Thank you.